In this video, I want to review some things about equations of lines in three-dimensional space. So let's just review lines in two-dimensional space. So these are the lines that you're familiar with. So here's the x-axis, here's the y-axis, and then if you have a line, okay, you could have a horizontal line, you could have a vertical line, you can have a line with a positive slope. Oops, that's supposed to be a straight line. Or you can have a line with a negative slope, right? And when you have a line with a slope, then the equation is going to be y equals mx plus b. And m is the slope, and b is the y-intercept. Well, technically, I guess the y-intercept should be the point on the graph of the line. So it's the point 0, comma b, right? And one thing that's missing with this equation is the vertical lines, because the vertical lines don't have this form y equals mx plus b. If you wanted the vertical line is going to be x equals a constant. And the way to combine this form and this form, so the vertical lines have undefined slope. And the way to combine these two equations of lines into one general form is to use the form ax plus by equals c. So this way, if you have a line with a slope, so of the form y equals mx plus b, if you just subtract mx, you get negative mx plus y equals b. And this has the form ax plus by equals c, right? So your a is going to be negative m, your b is going to be 1, and then your c would be b. That's how you match it up with ax plus by equals c. And then if you have x equals c, then that's just going to be 1x plus 0y equals c. So this is the general form of a line, is ax plus by equals c. That covers all the possible lines. And by the way, when we have this equation, we really mean the set, right? The line is the set of x and y satisfying the equation ax plus by equals c for those constants a, b, and c. This is the line is the graph of the equation. So the line is the graph of this equation. It's the set of points x, y that satisfy the equation ax plus by equals c. Now let's talk about, so that's lines, that's a review of lines in two dimensions. Now what about lines in three-dimensional space? Well, lines in three-dimensional space are a bit more complicated. And the reason is because when you have a line in three-dimensional space, like this, it doesn't have a slope. So it's a line that's going forever. Lines in three dimensions don't have a slope. So you're not going to have anything like y equals mx plus b, okay, where m is the slope, because there's no slope. That's a big difference. That's like the main difference between lines in three dimensions and lines in two dimensions. So what we're going to need to do to describe lines in three-dimensional space is we're going to need something called parametric. So instead, we need a parametric equation. And what a parametric equation is it's a function where the output gives you all the points on this line. That's a parametric equation of the line. And what lines have, instead of a slope, they have a direction. They have direction vectors. So if you take a direction vector of a line is just any vector that's parallel to the line. So if you take a vector like that, that's supposed to be parallel to the line, that would be a direction vector of the line. Or you could have a vector going in this direction, right? And there's no specified length. I mean, it could have length 1, it could have length 2, it could have length pi, right? So those are going to be direction vectors. So these two are direction vectors of this line. It's any, so i.e. a vector that's parallel to the line. And that's going to be our substitute for the slope. Okay. And if you have a point on the line, so let's go back to this example. Let's say you have a point that's on the line, and you have a vector that's parallel to the line. Let's call this vector, say, v. You can actually describe all the points on this line by this equation, r of t equals OP, so O is the origin, right? So you take the vector OP, which is this vector from the origin out to P, plus TV. OP plus TV. Okay, let's think about why that is true. So if you take t equals 0, then you get r of 0 equals OP, which is corresponding to the point P. If you take t equals 1, then you get r of 1 equals OP plus V. OP plus V, what's that? So you have OP, so you're here, and then you add V, and then the result is going to be this vector here, which is also on the line. And what happens if you take t to be -1? Then you get r of -1 equals OP minus V. So OP minus V is going to be, so you're using this V, you take -1 of that, so you're going to be like here, and you're going to get this point here. So you get all these points that are on the line. And as you vary t, as t ranges from from -infinity to infinity, that means ranges over all positive, not all positive numbers, all possible real numbers, you end up tracing out this line, the blue line. So that's why that's an equation for the line. Okay, let's do an example. So find an equation for the line that passes the points 2, -1, 3, and 1, 4, -3. So you have this point, okay, 2, negative 1, 3. I'm just drawing a picture to just illustrate the point. I mean, these aren't necessarily where the points are. And then here's 1, 4, negative 3. And you want the line that goes through these 2 points, like this. Okay, that's the line that we're looking for. And what we need is we need a point on the line. Well, in this case, we have 2 points on the line. And it doesn't matter which point you pick, just pick a point on the line. Let's say this one, 2, negative 1, 3. And we need a vector that's parallel to the line. That would be our v. So our v, we can take to be the vector from this first point to the second point. That's a vector that's parallel to the line. So we could take v to be 1, 4, negative 3 minus 2, negative 1, 3. And that's going to be negative 1, 5, negative 6. And so a possible equation of the line is going to be r of t equals 2, negative 1, 3 plus t, negative 1, 5, negative 6. Alternatively, so this is fine, but alternatively you can distribute the t across and then add the vectors. So then this will give you 2 minus t, right? Because when you distribute the t here, you're going to get negative t, 5t, negative 6t. When you add it to 2, negative 1, 3, you're going to get 2 minus t, negative 1 plus 5t, 3 minus 6t. So what these 3 components are telling you, this 2 minus t, negative 1 plus 5t, and 3 minus 6t, is it's telling you the point, it's telling you the x, y, and z coordinates of your point at the time, at t. So often we think of t as representing time. So where is the particle at time? Okay. Yep. And then one thing to keep in mind is, could we have used 1, 4, negative 3? Yes. You could also have used, so, well, maybe I'll just put a box around this to indicate that we have the answer. So this, alternatively, this is also fine. Okay. So that's the answer. And then an aside is we could have used uh, 1, 4, negative 3 also. And not only that, but we could have used a different v. So we could also have used okay, let's call this point P and let's call this point Q. So this is P and this is Q. So we took V to be PQ, but we could also have used QP, which is just negative V. Or we could have used any non-zero scalar multiple of V. Because all these vectors, it's not like you have to use this one vector specifically. If you scaled the vector by, say, a half, or scaled it by 2, or whatever, or negative 2/3, or whatever, all these vectors are parallel to the line. And that's what you need to get a direction vector. Did I explain that? Yeah, a direction vector of the line. Direction vector. You just need a vector that's parallel to the line. Any vector that's parallel to the line will work. And if you do this, so for instance, you could have used OQ, which is the vector 1, 4, -3, and then you could have used, say, the vector W, which is like -2V, and then that would have been 2, -10, 12, right? Because our V was -1, 5, -6. You multiply each of those components by -2, you get this. And then we would have gotten, so instead of R of t, maybe R1 of t, to indicate that's a second R of t. So you could have gotten 1, 4, -3 plus t to -10, 12. And then you would have gotten 1 plus 2t, 4 minus 10t, -3 plus 12t. Now this is also correct. If you plug in, if you take this equation, R1 of t equals that, and you imagine plugging in all the values of t, right, all the possible real numbers into this, and then plotting what you get, you would end up getting the same line. You would have still gotten this line. But it wouldn't have been the same values of t for this R of t and this R1 of t. So for instance, if you plug in, t equals 10 into R of t, then you're not going to get the same as if you plug in t equals 10 into R1, right? Because these are different equations. So these are different equations, but R of t and R1 of t are different equations. But they trace out the same line. So here's an analogy that I think might be helpful. So pretend that the line is like a freeway. So that's the line, and you're trying to find a parametric equation for this line. So a parametric equation, if you think of t as time and R of t as the position at time t, that's like a car on the road that's going along the freeway. So for instance, at t equals 0, you might be here. At t equals 1, you might be here. And at t equals 2, you're here. So if the car goes out forever, it's going to go forever along this line. And if you made t negative, so, 1 second before, right? So t equals -1, t equals -2, and you just make it go backwards, it'll go forever in the opposite direction. But that's not the only way you could have a car go on the line. You could have the same freeway, the same highway, but maybe you have a different car and you put your starting position, maybe your car is here at t equals 0. And maybe you want the car to go in this direction. So, you choose v to be this vector from here to here. So then when t is 1, the car is there. And, when t equals 2, you go the same distance in that direction, and then it just goes out forever in this direction. And then when t is negative, it'll be on this side, right? So like this might be where t is -1, this is where t is -2, etc. So they trace out the same line, but they, and by the way, just to make it clear, I'm drawing the same, these two are supposed to be the same line. So I guess if I moved it, oh yeah, it actually is pretty similar. Something like that. Okay. Hopefully you understand what I'm trying to say. You have like the same freeway, but you can make your car, if you need to make your car go along the entire freeway, you can choose where your car starts, and you can choose the direction that your car is going in. You can choose like how far it's going between t equals 0 and t equals 1, right? I mean, there's an infinite number of options. So you're going to get an infinite number of equations for the line, but you're going to trace out the same line. Okay. And that's the general, that in general is going to happen when you have these parametric equations, where you're describing the points on the line in terms of some parameter t. Okay. So let's try to connect. So this is different than the y equals mx plus b when you have a line in 2D. But you can also use, so you also have parametric equations for lines in 2D. So if you have the xy plane, let's just take a concrete example, and then I think you'll get the idea of what to do. So let's say that you had y equals 2x plus 1. So y-intercept is 1, slope is 2, so you're going to get this line like that, right? And how can you get a parametric equation for this line? Excuse me. Well, so you pretend that this line's like a highway, and you need to make your car go along the line, and you need to make it start somewhere. So why not make it start at the y-intercept? I mean, it doesn't matter. Well, the y-intercept's at 1, right, 0, 1. So we can make r of t equals, and now your r of t is going to have 2 components, right? Because before, we had 3 components. This is the x of t, that's the y of t, that's the z of t. It says what the x value is, what the y value is, and what the z value is at time t. Well, in 2D, we only have an x of t and a y of t. And one thing you can do is you can make the time just x of t equals t. So x of t can just be t. And then your y equals 2x plus 1. Well, if x is equal to t, then your y will be 2t plus 1. That's y of t, that's x of t. And do you see what's going to happen when you do that? When you make t equal to 0, you're going to get 0, 1, right? If you plug in t equals 0 here, so for instance, r of 0 is just going to be 0, 1. So here at this point, so this is corresponding to t equals 0. When t equals 1, that corresponds to x equals 1. R of 1 is going to be 1, 3. So that's going to be this point corresponding to x equals 1, right? That's when t is 1, and then when t is 2, you're at, make this go out a bit more. Oh, okay, like that. And then you're at this point. That's corresponding to t equals 2. And then that's 5, right? 2, 5, etc. That's how you can parameterize y equals mx plus b. In general, you can parameterize the line y equals mx plus b by r of t equals t, mt plus b. So you can have parametric equations for lines in 2D. Now, is there something like y equals mx plus b for a line in 3D? The answer is no. The closest you can get is you can use intersections of planes. So if you have something like ax plus by equals c, except with the extra z. So if you had something like, if you had ax plus by plus cz equals d, this is not an equation of a line. This is an equation of a plane in 3D. And we'll go over why this is true in a separate video. So it's not an equation of a line. Basically what happens in n dimensions, so this is the case when n is 3, in n dimensions, if you have a single equation like this, then the points form like an n minus 1 dimensional object. So when n is 2, 2 minus 1 is 1, you get a one-dimensional object, that's a line. When you have n equals 3, 3 minus 1 is 2, you get a two-dimensional object, that's a plane. And if you had, n is 1,000, and you had the points that satisfy an equation like this linear equation with 999 variables, no, it's 1,000 variables. If you have n equals 1,000 and you have this linear equation with 1,000 variables, then what you end up getting is a 999 dimensional space, like this object. And yeah, that's something called a hypersurface. This is an n minus 1 dimensional space in this n dimensional thing. And then to go back to the case of n equals 3, if you want a line, the best you can do is you can take two planes and intersect them, and then that will give you a line. So we really don't want to use this kind of thing for describing lines. We really prefer in 3 dimensions or higher to use the parametric equations. And again, the downside of the parametric equations is that there's lots of options for the parametric equations, right? There isn't really a standard way, like a standard form for a parametric equation. So that's kind of one of the downsides, but parametric equations are fundamental in multivariable calculus, and we'll be using it a lot. Okay, so let's just review what we did. So we reviewed lines in 2-dimensional space. Okay, the general form is ax plus by equals c, but we explained that lines in 3 dimensions don't have a slope. So you can't use, nothing like this, ax plus by equals c is going to work in 3 dimensions. Instead, you need parametric equations where you describe at each time t, if you think of t as time, describe it in terms of a single variable, all the points on the line. And it's, if you take a point p on the line and a vector that's in the direction that's parallel to the line, then you are going to get OP plus TV, where t ranges over all the real numbers. And we did some examples, and we saw that any line is going to have an infinite number of parametric equations, just like if you have a freeway, there's an infinite number of ways a car can traverse the entire freeway. That's like an analogy. And then we explained how to come up with parametric equations for lines in 2D. It's really easy. If y equals mx plus b, it's just r of t equals t mt plus b. That's one way to do it. That I think is the easiest way to do it. It's not the only way, right? Because you can just have any vector maybe I should clarify what my p and my v would be here. So this would be 0, 1 plus t 1, 2, right? So just to clarify, this would be my OP, like here's my O, this would be my P, and then this vector is my V. So that's my R of t. So you have the same thing. You can do parametric equations for lines in 2 dimensions, not just 3 dimensions, and you can actually do it in any number of dimensions. That's the other benefit to doing parametric equations. It works for 500 dimensional space, and yeah, and then in a later video we'll go over why when you just extend the y equals mx plus b, or ax plus by equals c, that's in 2 dimensions for lines, and just add a cz to make 3 dimensions, why that's a plane instead of a line. Okay, thanks.